There is a hole in the hull of a cruise ship. Water is pouring in, and the ship is not sinking. That sentence should be impossible. A steel vessel the size of a city block, floating on open ocean, develops a breach in its hull and simply continues floating. The instinctive explanation most people reach for is size. The ship is so enormous, so massively built, that a small hole barely registers. The steel must be so thick, so industrial, that water can't meaningfully penetrate it. Both of those explanations are wrong. The steel hull of a large cruise ship is not an impenetrable fortress. It is not kept safe by brute thickness. A cruise ship is not a sealed container. It is a deliberately divided system, engineered from the earliest design phase to flood in a controlled way. The ship survives a hull breach not by keeping water out. It survives by managing exactly where that water goes. That is the real answer. And it is a completely different kind of answer than most people expect. Here is what is actually inside a cruise ship hull. Not open space, not a single enormous chamber. The hull is divided, vertically, systematically, by a series of transverse steel walls called watertight bulkheads. These are not thin partitions. They are structural walls that run from the bottom of the hull upward through multiple decks, sealing each section of the ship from the sections beside it. The hull is essentially divided into dozens of separate watertight compartments, end to end. Think of it less like a ship and more like an apartment building lying on its side. Each unit is sealed from its neighbors. If water enters apartment 4, apartment 5 stays dry as long as the wall between them holds. That analogy is not quite right either, because the goal is not simply to keep the compartments sealed forever. The goal is something subtler and considerably more interesting. The question is not, why doesn't the ship sink when a hole appears? The real question is, who decided which rooms flood, and when, and how many? Long before that ship ever left the shipyard, the answer begins with a document most passengers will never hear of. The International Convention for the Safety of Life at Sea, known as SOLAS, is the regulatory treaty that governs the design of passenger ships worldwide. Under SOLAS, a cruise ship is not permitted to enter service unless it can demonstrate something very specific: that it will remain afloat and stable even after certain compartments have flooded. For modern passenger ships, the standard generally requires surviving the flooding of 2 adjacent compartments simultaneously. Larger, newer ships are held to even tighter standards. Every watertight bulkhead position in the hull is not chosen for aesthetic or structural convenience. It is mathematically placed to satisfy a calculated survivability score, what naval architects call the required subdivision index R. That index is a probabilistic figure. It does not say the ship will always survive every possible breach. It says the ship has been engineered to survive the most likely and most plausible configurations of damage, and that the probability of surviving those scenarios exceeds a mandated minimum threshold. In other words, the ship is not built to be unsinkable. It is built to survive, statistically, the most probable ways it could be hurt. The first mechanism making that possible is the bulkhead system. When flooding sensors detect water in a compartment, automatic watertight doors throughout the ship activate, sealing adjacent zones and cutting off the spread. This does not happen slowly. The system is designed to react faster than the flooding can cascade. Water enters a compartment. The boundaries of that compartment close. The breach is contained. The second mechanism is the double hull. A modern large cruise ship does not have a single layer of steel between the ocean and the interior. It has 2, an outer hull and an inner hull with a void space between them. When a reef or rock strikes the ship, it may breach the outer hull entirely, and the inner hull remains intact. That space buys time. It limits the volume of water entering per minute. It is the difference between a manageable emergency and an immediate catastrophe. But here's the first important reversal. The bulkheads are not designed to permanently hold back the sea. They are designed to hold long enough. The system does not aim to stop flooding indefinitely. It aims to preserve enough stability and buoyancy for the ship to remain controllable long enough to stop, assess, and evacuate. It is a delay mechanism. The survival window is built into the design specification, and that changes what the system actually is. It is not armor. It is time. Reserve buoyancy is the third layer. A cruise ship contains significantly more enclosed hull volume above the waterline than the absolute minimum required to float at its operating weight. That excess volume is deliberate. When one or two compartments fill with seawater, the ship sinks slightly deeper, but it does not sink. The remaining enclosed volume maintains enough buoyant force to keep the ship on the surface. The lost compartments reduce the margin, they do not eliminate it. This is engineering as a budget. The designers begin with a surplus, more buoyancy than the ship needs under normal conditions, and the damage stability calculations determine exactly how much of that surplus can be consumed before the ship's situation becomes unrecoverable. Floating, though, is only half the problem. A ship can have perfectly adequate reserve buoyancy, enough that it will not sink and still capsize. Staying on the surface and staying upright are two entirely separate engineering challenges. And the second one is governed by a quantity that most passengers have never heard of: metacentric height, abbreviated GM. Here is the intuitive version. When a ship is tilted, by a wave, by wind, by flooding on one side, something has to push it back upright. That restoring force is not mystical. It is geometry. As the ship heals, the underwater shape of its hull changes. The center of buoyancy, the geometric center of the volume of water displaced, shifts sideways toward the lower side of the ship. That shift creates a righting moment. The buoyant force and the gravitational force are no longer aligned, and the imbalance works to push the hull back toward vertical. The metacenter is the theoretical point where that righting geometry converges. If the metacenter sits above the ship's center of gravity, the ship is stable. The restoring force is self-correcting. The ship rights itself. If the center of gravity rises above the metacenter because cargo is loaded badly, because fuel tanks drain unevenly, because something shifts, the same geometry runs in reverse. The imbalance now pushes the ship further over instead of correcting it. That is a negative GM. And a ship with a negative GM does not roll back. It capsizes. Cruise ships manage this carefully. Engines, machinery, fuel, ballast. All the heaviest systems are positioned as low in the hull as physically possible. This keeps the center of gravity, G, low, and the metacentric distance, GM, safely positive. At the same time, everything passengers see, the vast superstructure, the upper decks, the pools, the restaurants, stacked 15 stories above the waterline, adds top-heavy weight that designers must perpetually counterbalance against the machinery below. A cruise ship is, among other things, a constant negotiation between the weight the revenue model demands above the waterline and the stability physics demands below it. Now introduce a flooding scenario. A compartment on the starboard side fills with water. The ship develops a list, a lean toward the damaged side. That lean shifts the effective relationship between G and M. A moderate list can become dangerous, not because the ship runs out of buoyancy, but because the lean itself begins degrading the metacentric stability. If the list reaches a critical angle, the righting geometry inverts. The countermeasure is deliberate and counterintuitive. Controlled flooding of the compartment on the opposite side of the ship. You let more water in, intentionally on purpose, to level the vessel and preserve the GM. The ship survives by taking on more water than it would have otherwise. That is the system at work. Flooding to survive flooding. If this kind of investigation, pulling apart the real mechanics underneath something that looks simple, is the kind of thinking that interests you, subscribe to this channel. That is what this channel is built to do. Find the machine underneath the familiar surface and run it until it makes sense. On January 13, 2012, every layer of this system was put to the test, and one layer failed. The Costa Concordia was a 114,000 gross ton cruise ship carrying 4,252 people on a Mediterranean voyage. That evening, Captain Francesco Schettino ordered an unauthorized close approach sail-by of Isola del Giglio, a small Tuscan island. The ship deviated from its planned route. At approximately 9:45 p.m., the Concordia's starboard side struck the Lascaux Reef. The collision opened a gash approximately 70 meters long in the hull. 5 contiguous watertight compartments flooded. Simultaneously, that number is the entire story. The Concordia's damage stability design, based on the SOLAS standards applicable at the time of her construction, was calculated to survive the flooding of a specific maximum number of adjacent compartments. 5 contiguous compartments, including the engine room and electrical switchboards, exceeded that design envelope. Power failed. Propulsion failed. The ship developed a growing list to starboard that the crew could no longer counteract. Within hours, the list reached an angle at which lifeboats on the high side could not be safely deployed. 32 people died. Here is what the Concordia disaster actually demonstrated. It was not that the safety system was defective. The watertight bulkheads performed as specified. The automatic doors closed. The reserve buoyancy behaved as calculated. Every system did what it was designed to do. The ship was designed to survive a defined range of damage scenarios. The reef produced a damage scenario that fell outside that range. The system worked. The damage exceeded the specification. That distinction matters. The ship did not sink because the design was wrong. It sank because one human decision, a captain ordering a closer approach than the navigation charts could safely support, generated a physical outcome that no realistic survivability specification had been engineered to absorb. The maritime industry absorbed that lesson and changed the rules. In 2017, the International Maritime Organization amended SOLAS, amendments that became effective in 2020, raising the required subdivision index for new passenger ships. Future ships must demonstrate survivability against more severe flooding scenarios. The margin was widened. The specification moved closer to the edge of the realistic worst case. This is not unique to ships. The same probabilistic containment logic appears in aircraft fuselage design, in nuclear containment architecture, in data center redundancy systems. Every engineered system that must remain functional under damage is built around the same question. What is the realistic range of failures? And how do we survive the most probable members of that range? The answer is always a margin, a surplus of resilience engineered into the system above the baseline minimum, combined with a clear understanding of where that margin ends. The Titanic illuminates exactly this principle from the other direction. Titanic had watertight bulkheads. She had a compartmentalization system that was, for 1912, genuinely advanced. But the bulkheads did not extend to the full height of the upper decks. When the bow took on water and began to sink, the flooding crested the top of the forward bulkhead and poured into the next compartment. Then the next, then the next. The ship was designed to survive 4 adjacent compartments flooded. 5 flooded. The margin was 1 compartment. The margin ran out. The difference between Titanic in 1912 and a modern cruise ship is not a different kind of engineering. It is more engineering of the same kind, more compartments, higher bulkheads, a double hull, a formally calculated subdivision index, regulatory minimum standards, and ships large enough that losing 2 full compartments still leaves enormous reserve buoyancy intact. Royal Caribbean's Icon of the Seas, launched in 2024, stretches over 1,100 feet and displaces more than 250,000 gross tons. The buoyancy reserve in a vessel that size is not a comfortable margin. It is a designed-in architectural surplus, calculated compartment by compartment before a single steel plate was cut. So, when the question is asked why doesn't a cruise ship sink even with a hole in the hull, the honest answer is that the ship was designed years before it sailed to absorb that hole. Naval architects identified the most probable breach configurations. They placed bulkheads to contain them. They calculated the reserve buoyancy required to outlast them. They positioned ballast and machinery to maintain a positive GM through them. They built a double hull to slow the initial ingress. And they codified the whole architecture into a regulatory framework that every passenger ship must satisfy before it is permitted to carry a single person to sea. The hole in the hull is not the threat the question assumes. The ship was never a sealed container trying to keep water out forever. It was always a probability machine, designed to survive not the absence of damage, but the presence of specific, realistic, calculated damage. Every bulkhead is an answer to a damage scenario someone already considered. Every void space in the double hull is a buffer, engineered into a design specification. Every automatic watertight door is a delay mechanism holding open a survival window. And the ship floats not because it is unsinkable. It floats because the engineers, long before launch, sat down and worked through every plausible way it could be hurt, and built the answer in before anyone ever stepped aboard. I hope you enjoyed the video and learned something new about one of the most fascinating engineering marvels ever built by mankind. If you want more content like this, please subscribe and hit that like button. I'm Larry, and this is the Ship Files. Thanks for watching, and I'll see you in the next one.